Okay, for this review problem, let n be an integer. We're going to prove that if n is greater than 2, then n squared minus 1 is composite. Okay, so let n be an integer. So that n is greater than 2. I want to show that n squared minus 1 is composite, which means that it has a factor other than 1 or itself. Okay, so first off, n squared minus 1, then n squared minus 1 is going to be greater than or equal to 8, right? That's the smallest it could possibly be. If n is greater than 2, then n squared minus 1 is greater than or equal to 8, and so n squared minus 1 does not equal 1. So that's the first condition for a composite number, that 1 is not composite. N squared minus 1 is not equal to 1. Second, we have to show that n squared minus 1 has a factor other than 1 or itself. Also, using the difference of two squares, n squared minus 1 is equal to n minus 1 times n plus 1. Since n is greater than or equal to 3, both n minus 1 and n plus 1 are greater than or equal to 2. So first things first, both of these numbers are greater than or equal to 2. Also, they're not going to be equal to the original number. Also, n minus 1 will be equal to n squared minus 1 over n plus 1. The bottom here is greater than or equal to 2, which means this is less than or equal to n squared minus 1 divided by 2, which is less than n squared minus 1. In particular, n minus 1 cannot be equal to n squared minus 1. So n minus 1 is not equal to 1. Also, n minus 1 is not equal to n squared minus 1. Finally, by the axioms of arithmetic, n minus 1 and n plus 1 are both integers, since n is an integer and also 1 is an integer. So I have established that n squared minus 1 has a number, n minus 1. n minus 1 is a factor of n squared minus 1. Also, n minus 1 is not equal to 1, since it's greater than or equal to 2. And also, n minus 1 is not the original number. So by definition, they're both integers. So by definition, n squared minus 1 is composite. And so that's the end of the proof. So a little bit, some technical details here. We showed that there was fit factored, but I had to also show that the terms, that the n minus 1 here is not equal to 1, also not equal to the original number. Now, what happens if n equals 2? If n equals 2, then 2 minus 1 is 1, and so it doesn't work. If I plug in 2 here, I get 4 minus 1 is 3, and that's prime. So the theorem is false if n is equal to 2, but if n is greater than 2, then the theorem is true, because n minus 1 here is going to be something that's greater than 1. So that's the proof of this theorem.